All right, welcome everyone. I think we're gonna get slowly started. There is already 30 attendees here. People should actually join on the flow. As I said, we were actually waiting for the latecomers to actually just join us as a last minute. Yeah, there is actually people incoming a bit all the time. Thanks for joining this 2021 session. I think, Guillaume, we can get started. What do you think? Is that fine for you?
Yeah.
Perfect.
Ready.
So thank you everyone for joining this 2021 edition of the SOFA Week. We're actually quite happy to welcome you, whether it's actually the morning, the afternoon, or maybe even for some of you it's going to be the start of the evening. So for this 2021 session of the SOFA Week, and you'll discover actually various presentation topics of research and developments that are occurring around SOFA. You'll discover the latest achievement, some of them just recently published work. So I hope you'll enjoy it. And let me show you a bit the program for today. So we're on the 23rd of November. It's what we call the International Symposium of SOFA. Again, it's the day of the SOFA Week where we are actually gathering and getting all the presentation of both academic and industrial work done around SOFA. Tomorrow, just so that you know, tomorrow there will be also the technical committee, which is the next step and the last event of the SOFA Week, which aims at working together around the roadmap of SOFA, meaning making a bit the summary of what has been done in the last 6 months, talking about what's going to happen in the next 6 months, and then discuss about the various development technical topics. So if you are interested to discover actually how the roadmap of SOFA and how the project is on the development side, driven and managed, do not hesitate to join us. It's going to be tomorrow starting at 9. And yesterday, for the opening of the SOFA Week, there was, for the first time, a satellite event that was the workshop Driven. And Driven is actually a European project that is around data-driven simulation. And we have five quite interesting talks around simulation and data-driven simulation, obviously. So do not hesitate to check out the program of yesterday. And obviously, all the yesterday, today, and the next day's session will be recorded and available soon on our YouTube channel. So for today, about the symposium, let's start a bit with a bit of history for the ones that are actually a bit new to SOFA in the audience. SOFA, as you may know, it's a project that started back in 2006 in a research center which is called INRIA, which is a French research institute for computer science. And back in 2006, there was actually several teams already. It was not only one team of research, but actually 3 teams that needed a collaborative tool to build physics simulation and build physics simulation for already different purposes. Some of them were for computer graphics, for some of them it was medical simulation already. So already various topics, but one common tool, and that's what gave actually the core of what SOFA is today, which is the project definition of SOFA, which is being an open source reference for interactive and real-time application. As I'm always saying in the training sessions that we have around SOFA, I would say the main keyword of this project definition is definitely the keyword interactive. Obviously, we are open source, that you know that already, but the keyword is really the interactivity, which is I think one of the main strengths of the SOFA project. SOFA, it's a physics engine, and as a physics engine, it implements models and algorithms to actually solve those laws of physics, namely mostly mechanical laws like soft and rigid body dynamics. And we are using those simulations for various topics. You are actually using SOFA for various topics, which are medical simulations, robotics, soft robotics, also more recently in the last years, which have been extensively expanding, significantly expanding. Augmented reality, virtual reality applications. We're going to have some examples today as well. Animation, computer graphics, and also some guys are working in the audience on biological application with SOFA. Since the beginning, the concept of SOFA was the following 4 keywords. The fact that we wanted a flexible framework where you are able actually to design easily in a quite short amount of time a new simulation and possibly change it, make it evolve with quite low effort using scripting methods like XML and more recently Python scripting, which is also easing and expanding the potential of SOFA simulations quite a lot. Second, we wanted to have a flexible and a modular architecture, architecture, because SOFA is actually following a model which is called an open core model. We have an open source core, and around this core, you are, as an academic or as an industrial, developing additional features that can be open source or closed source. And finally, the two last points are actually going together. The fact that we wanted to have an interactive framework, being able to take into account the user interactions, for instance, to be able to modify the scene on the fly, to enclose also SOFA in some optimization loops. We're going to see some examples today. And for that, we needed to have actually an efficient framework, efficient to solve the matrix linear problem that we have, and also using multi-threading and GPU computing. So as you might know, SOFA has a license as any open source project, and its license is LGPL, which provides you actually the freedom to download, use SOFA, that you might have already done it, modify SOFA, that is most welcome. I mean, you can definitely modify SOFA, and you can even contribute back to SOFA, and you can make your research and make possibly products based on SOFA freely. That's the freedom that gives actually the LGPL license. The philosophy that comes also with the LGPL license is the fact that when you are improving something which is of a common use, like in the core of SOFA, it's always most welcome to contribute that back. So never hesitate to make also contribution back to SOFA. All the code is obviously available on GitHub, that you might also know already. That's I'm just giving here the GitHub link of the SOFA project. And SOFA is made, and again, you might have discovered that, mostly C++ classes. The everyday development is actually managed through GitHub, as we just saw in the previous slide, using Git versioning system. And this, for I think the last 4 or 5 years, changed quite significantly the way we are actually developing with SOFA. We are following really a real what we call peer review process, which improves, we think, quite significantly the robustness of the project. We hope you do share actually this vision. And thanks to actually Guillaume who is actually with me here on stage. It's new versions of SOFA are actually released every 6 months, and we are trying our best to make those new releases of SOFA first cleaner, more robust every 6 months, and also with new improvements and possibly a more efficient way of developments, especially for working with SOFA and your plugins. That's things that will be discussed actually tomorrow at the technical committee. So as you might know, so the current stable version is the 20.06, and soon, obviously, in 6 months, it will be December. So v21.12 will be the next release, so coming soon. We have this stable core, and as I said, around this core, plugins, that's where all of you guys are actually coming in the game, building optional features, building new models, new algorithms into your own plugin. You are the one to decide what is the license of your plugin. You are the one to choose. So choose the license that suits you at best. But definitely never hesitate to let us know about what you are doing, whether it is open or private. It's always helping for building the community and making networking within the SOFA environment. We're going to get back right after lunch. It's going to be at 1:15 p.m. CET. So right after lunch, we're going to talk again about the community shortly. But here is a short look about the I would say, percentages of the community SOFA, which is being developed for 15 years now, and still mostly academic, but something which is growing more and more. It's actually the number of first startups built around SOFA, the number of companies involved around SOFA, and the number of independent developers. That's really something which is a very good for us, a very good indicator of the health and the I would say, yeah, the good ongoing of the project. For today audience, we have actually more than 180 people that registered for the event. Obviously, it's going to be smoothed over the day, depending whether people are in Asia, Europe, Australia, Africa, or America. So that's gonna be the audience for today, coming from 32 different countries. Let's get to the point. which is namely the program of today of the symposium. We're going to have a lot of different presentations on various topics. And for this morning, it's going to be firstly soft robotics. And then we're going to look at numerical methods for simulation. And compared to last year, for instance, numerical methods for simulation, that's also a topic which, just like robotics actually, and soft robotics, topics which are growing of interest in the community, where more and more people are actually working on. So we're going to start with soft robotics. We're going to see how actually soft robots are self-healing. We're gonna see also micromanipulation of soft robots, as you can read, parallel continuums robots, and evolving robots depending with different kind of actuators, and in that case here, fluidic actuators. And then we're gonna move to more numerical analysis topics with the numerical methods session. So I see that Pasquale is already ready to start. Welcome, Pasquale. Thanks for joining and applying for presenting your work this morning. Just before starting, I'd like to again just explain how it's going to work. Each presentation is going to be 15 minutes. Those 15 minutes are going to be somehow divided in, I would say, 10, 12 minutes of presentations. We'll keep a bit of time for having one, two questions for the speakers. But then at the end of the year 4 presentation of the soft robotics session, we're going to have one dedicated time, which is actually 20 minutes, so quite a lot of time for discussions in breakout rooms, so specific sub-rooms where anyone in the audience will be able to join, for instance, Pasquale, which is with us here, but all the different speakers to ask all the questions that you did not have the time to ask, or propose collaborations, or proposing sharing code or whatever. So basically, talking from the topic of interest for 20 minutes in specific rooms. That's going to be the break time for meeting the speakers, and there are going to be one specific break and breakout rooms with discussion times after each session. And I think it's going to be the last word before really starting the interesting, I would say, presentation with Pasquale. There are going to be an award ceremony. There have been actually people contributing to SOFA, and that applied for the SOFA Awards, 2021 SOFA Awards. So do not hesitate actually to vote, because there is 2 different prizes. First, the organizer's prize, what I'm going to present that after lunch, and the public prize. Presentation of all the different contributions will be done again at 1:15 right after lunch. But by then, and before then, do not hesitate to go online. We're going to put we're going to copy paste the link here in the chat. Go online and vote for the contribution that appears to you being the best contribution of this 2021 edition of the SOFA Awards, and we're going to rediscuss that a bit later on. First things first, soft robotics, which is again definitely one of the main topic of simulation in the community, which is growing. I think one of the first team was the Christian Joyeu's team, the SOFA Defrost team that was really working on the topic, and now it's definitely a worldwide topic. We're going to have here examples coming from Belgium, coming from different parts of the world, as you can see. So Belgium, France, and South Africa is going to be for today. And we're going to start with Pasquale talking about self-healing robots. Pasquale, are you ready to start?
Yes.
Perfect. Let me know if you can properly share your screen. And obviously, anyone in the audience is welcome to post question in the chat, whether it is a technical question about the voting process for the SOFA Awards. If you have a question for the speaker, do not hesitate to drop it as well in the chat. We would be happy to actually then forward the question to Pasquale, or obviously you can just unmute yourself at the end of the presentation and ask all the details that you'd like to know about Pasquale's work. And it will be the same for Maxence, for Benjamin, and for Michael.
Is that fine for you, Pasquale?
For testing, can you hear me?
Yeah.
I needed the animator role, but can you still present Pasquale if I take this role?
I don't think so.
Okay, so let's move on.
Yeah, go ahead. You should be able to reshare your screen, I think, Pasquale. And...
Yeah. Is it that is connection in? Yeah, I don't know. because
We'll let you know.
Wait. Yeah, I mean it's like loading, but it's not doing nothing. So I don't know.
Okay. Can you just restart? I mean, just stop the sharing and restart just to check.
Yeah, but there is not a button to restart. It just frozen like that. So understand.
Okay. Yeah. Can you maybe, Guillaume, retake the role and give that back to Pasquale, or?
Actually, you shouldn't need the role to share. Everyone can share, so the role is meaningless.
I don't know, maybe I don't know. Maybe I will rejoin to the I will restart.
Please go ahead.
Okay.
Just in case, Maxence, are you around? I'm gonna check in the audience. Here, yeah, perfect. I see. Okay, cool. Well, we're just gonna wait, Pasquale, for reconnecting. If there is any issue, maybe I'm gonna ask you to take the first seat. Okay.
No problem.
Thanks a lot, Maxence. All right. Welcome back, Pasquale.
Okay. Okay.
Yeah, we see a screen sharing starting. We can't see for the moment.
Okay.
Yeah, perfect.
Yes.
We see ourselves.
Okay. So now you see my presentation.
Yeah. Yeah, you can go full screen now.
Okay.
Perfect.
Okay.
So thanks for opening this session,
everyone.
Pasquale. Pasquale, which is working. Yeah. Go ahead, Pasquale. I'll let you the floor.
Okay. Thank you, everyone. Sorry for the problem in the sharing the slides. I am Pasquale Ferrentino. I am a PhD student at VUB University in Brussels, Belgium, and I belong to the robotics, the Human Robotics Research Center. And today I will present the modeling and control of self-healing soft robots with SOFA. And the results that I will show to you are recently accepted to the IEEE Robotics and Automation Magazine journal. But before to start to showing the results for my research, I want before make an introduction on what are these polymers, these self-healing materials. Actually, the materials that we use in our lab are called DL-Salder polymers, and they are made by a thermoreversible network. That means that the crosslinks that are in the polymer chain can... What?
You go ahead. No. Okay. It's perfect. Fine. Go ahead.
As I said, there are thermoreversible polymers. That means that in the polymer chain of this material can be rebuilt and destroyed by after a heat treatment. So that's why these materials are called also self-healing, because can recover without making scars and so on. Also macroscopical damages. And why we use actually we do mostly soft grippers with these materials. And why we use this material, because it's very easy to fine-tune the mechanical properties. In fact, we can reach medium to high mechanical strength. He can resist to unlimited healing cycles, also because it's easy to reprocess and recycling. So also is a green solution for soft robotics. Actually, we as group are involved in 2 European projects that are the Shiro and SMART. And also, of course, someone have a personal grants with FWO, the Flanders Research Funding. And actually, we are able to make a multi-material design, joining our self-healing material with other self-healing material or other normal material, not self-healing polymers. Or we are also able to make self-healing sensors. That means that our materials that are self-healing, but also conductive. And of course, also self-healing heaters that are self-healing, material that are self-healing, but also thermal conductive. And actually, yeah, I'm mostly working on the FEM modeling of this material. Yeah, on the robot that we make on this material. But I have also other colleagues that are trying to do voxels with the same material that we use, so voxel-based robot. And also are the people that are working on additive manufacturing, so making 3D printable this kind of material. And here we are. Actually, in the view B, there are 2 departments, 2 labs that are working together. The robotics, where I belong, that is mostly take care of robotic part, and the FISC, that is a material science lab, so take care of material production and polymerization. And now we can start with the results that I had as a first preliminary work on modeling of this material using SOFA. And actually, the results are organized in this structure. I start before with a material characterization. Actually, we will make some static tests, tensile test, and compression test on the material. Then we will make an hyperelastic modeling fitting the experimental data from this compression and tensile test. And then, of course, the material constant that obtained from this constitutive model, fitted constitutive model, I will put in SOFA and make the simulation, let's say, the model. And of course, this model will validate with experimental data, and I will produce finally an inverse controller. Yeah, actually, by literature, to make a very accurate hyperelastic modeling, you need 6 different static tests on your material that are the anaxial one, in tension and compression, the biaxial, and the planar that are also the shear. Yeah, they're also called the pure shear test on the material. But of course, these machines are not. You cannot find this machine in every lab. And actually, we just used the tension and the compression, and we obtained the strain stress curve. And the results, yeah, the experiment was conducted at 1% of strain ramp. So then what I do, I go in Abacus, and in Abacus there is an internal plugin that can accept in input the data from your machine, from tensile and compression test, the strain stress curve, and on it can fit some hyperelastic models. And here we tried actually 5 different hyperelastic models that are the Neo-Hookean, the Muller-Rivlin, the Ogden, the first, the second order, and the Yeo. And of course, between them, we have to find the one that fits better our curve. And first of all, we have to apply a mechanical condition to this on the strain energy function of the hyperelastic models that are called Tucker stability. And as you can see, just the Neo-Hookean and the Ogden are stable for all strains, so respect fully for all the range of strains that we tried in the tensile stress, the Drucker stability, while the others are not stable. I mean, are stable just in the range of the curve. So we discard this the latter one, and we conserve just the Neo-Hookean and the Moonlay had the Ogden first order. And of course, Abacus use a Levenberg-Marquardt algorithm to do the fitting. So we have to check the normal residuals, the root mean errors of them. And you can see that the two models are quite equivalent. But of course, for Neokian is just a bit more precise. And for terms of computation, Neokian is much lighter than Ogden. And we obtained from that also the material constant. And so we consider the material as Neokian in this. So we also make another experiment to make the model robustness, but also the material robustness. We just take a tensile specimen of the material, we test it until fracture, we heal it, and we test again. So I will repeat this procedure for 5 times, and because we want to see if refitting the Neokian model for each of let's say healed specimen, we have the same material constant. How, let's say, just to evaluate a bit what is the healing efficiency, and if our material lose mechanical mechanical performance during the healing. Actually, the most important parameters, you can see the material parameter C10 and D1, that between the undamaged and the healed one are almost the same. Also for the compressibility factor. And of course, we measured also the fracture stress, the fracture strain, and we make also the healing efficiency. And for the stress and for the strain are the 96% and 91%. So the efficiency of the healing is almost doesn't lose any mechanical property after 5 healing cycles. And another interesting point is that the fracture location is not the same at each healing cycle. That means when you heal the material and the surfaces that are damaged, that are in contact, that are healing, they are not the weakest point of the material. So at the following, let's say, tensile test, we will break in another point. So after that, we measure we do the SOFA simulation. We just consider a Pienaar design. We also realize it with injection molding. And my simulation contains 64K tetrahedrons. I use a Euler implicit solver and a sparse LDL linear solver, so the classic one. And we want to validate this model, that the results from the simulation with the real experiments. So I also created a simple actuation setup that is just a syringe coupled with a stepper motor. And then we have an RGBD camera that is for motion tracking. In fact, the method is to put 9 blue markers on the Pienaar SoftRobot. And then in the simulation, I select, a node in the same region when I put the markers. And so in the simulation, I will retrieve the bending angle and the position. And from the camera, using some segmentation and clustering algorithms, I can obtain the centroids of the markers, so the positions of the markers. And also I calculate the bending angle as in figure A, with a fixed reference frame and the position of the last marker. These are the results. Actually, we test, we make multiple tests on that with different pressure inputs and different orientation with respect to gravity. So as you can see in the central figures, and on the left, you can see the final configuration at different pressure inputs, and you can see the position of the markers detected by the camera, and of course the position of the nodes that detected in the FEM simulation, in SOFA simulation. And we calculated the root mean square error for these 3 final configuration. That is less than 1 millimeter. So we can say that, let's say the simulation match the reality. And also, yeah, on the right, we estimate the bending angle for all the experimental, for the camera experiment, the real experiment, the film simulation. And let's say that the two bending angles in the two cases are converging during the experimental time.
Yeah, you have like 1 minute left, Pasquale, if it's fine for you.
Yeah, I finished.
Okay.
It's just the last part. Then I make the inverse controller. I pass the simulation with the model order reduction. And of course, I use the SoftRobot inverse plugin, and the frequency is to 20 Hertz, the velocity of this inverse controller. And then, these are the results. I tested the finger with the undamaged configuration with the 2 healing cycles, and the results, I made just the step response as controller. And the results is that also after 2 healing cycles, after 2 big damage, the robot still converge to the same point in the controller. And this is the just last results. Then there are the conclusions. It's a bit so summary. So we started from the mechanical test. We fitted the hyperelastic models, and we also checked the robustness of this fitting. And then we do the simulation that is validated with reality. And after this, we check that is validated. We make the quasi-static step response controller. And then of course there are some future works that maybe we can discuss after with people that are interested to collaborate and something like that. And here there are just some let's say some principal publication that we had, and some contacts to, if you are interested to collaborate with us. And thank you for the attention.
Thanks a lot, Pasquale. Can you get back to the slide for maybe the next, the next step, so that we can keep this one under under the nose, so that people can see a bit what's going to be the next steps. Is there any question in the meantime for Pasquale?
Yes.
And if so, do not hesitate to unmute yourself. It was the 20, the slide number 20, I think.
Pasquale, can you hear me?
Mm-hmm. Yeah.
I had a question. Do you plan to model the cutting and the fact that you can like the relationship between
actually I put this in the
this is the goal at the end?
Yes, actually I put this in the future works, but actually is a long plan for my PhD, or let's say also a postdoc, because now we are just started to make soft robots, so we want before understand what are the mechanical properties of our materials doing soft robotics. But for sure, let's say in 2-3 years, we want also to be able to control all the self-healing process. That on material side, they will study the kinetics of this mechanism. And maybe in SOFA, we can also, I would like to have, let's say, a plugin that you can cut the radial mesh, then you can hit the finger, let's say, the polymer, and also to regenerate the mesh, also to have something like a spring of, like that. After the cut.
Thanks a lot. For question for Pasquale, it's we're gonna meet in a few minutes. So after the 4 different presentation on soft robotics, we're gonna meet in a specific breakout room at 10:30, around 10:30, and you'll have 20 minutes to discuss with Pasquale about self-healing material and self-healing soft robots. So thanks a lot, Pasquale, for the presentation. We'll move to the presentation of Maxence. Maxence, are you around here?
Yeah, I'm here.
Perfect. You should be able directly to share your screen and start your presentation.
Okay.
I'm just deactivating my camera for letting more bandwidth for you. So yeah, perfect. We see the slides.
Okay.
So please go ahead, Maxence. The floor is yours.
Thank you. So welcome everybody. I'm Maxence Leveziel. I'm a PhD student at the FemtoST Institute in France, and today I will talk about the modeling of soft jointed miniaturized robots in the context of high-speed micromanipulation. So first of all, some microscale robot challenges. So we know rigid robots such as this one, and there is few examples of miniaturized parallel robots in the world. We have this example from the Harvard University from 2018. And the fact is this robot is a folding joint, so it's unidirectional joint. And in the other end, we have also the continuum on soft parallel robots with almost an infinity of degrees of freedom. And what we are trying to do is to merge rigid parallel robot and continuum soft parallel robot in one structure in order to have something closer to a spherical joint in rigid modeling. So we design a parallel robot with a silicon part which act at rigid links and PDMS soft joints. And the aim is to model those joint. So in this context, we design we have done a simulation with a simplified model, so it's only planar, and we have 5 silicon element and 4 PDMS soft joint. And the question is how to model and control this kind of structure. And there is some constraints, such as the materials. We can see that there is a huge difference in the Young modulus between silicon and PGMS, which can lead to some numerical problems. And also the percentage ratios of the PGMS, which is close to 0.5, and also can lead to some numerical problems. And other constraint is the fact that we want to have fast simulation, mainly under a second, and the joints are used in large deformation, and it's also very important to plot this. So basically what we are trying to do is to compare some models in order to know which one is the more accurate, to find the best compromise between accuracy of the model and I would say speed of the model. And we have done some simulation with ANSYS workbench, which will act as a benchmark for the rest. And we have done fine mesh, a cubic mesh with a 0.04 millimeter element size, and another with a cubic mesh with 0.08 millimeter element size. And after we compare those results with a SOFA simulation with the same cubic meshes in order to know the accuracy, and also the beam from the SoftRobots plugins and beam adapter, and also some rigid modeling when it seems suitable. So what we've done, so we consider the structure I presented before, and we are doing a variation of the percentage of soft element in the line. So we begin with 10% and we go to 100%. So in the case of 10%, we have a 0.4 millimeter soft joint at each extremity of the rigid link. And so we've done this kind of modeling for finite element. After we consider a 1D beam representing the cubic joint, and also a rigid modeling with the center of the spherical joint corresponding to the center of the real joint. And what we can see is for 10%, the results are quite similar for each models. And for the error, it's around 10% for each model for SOFA and rigid modeling. And we can see there is some quite strange results is because of there is points of very huge, large deformations for the 10% soft element. And after, if I move to 20% soft element, what we can see is that the rigid modeling still suitable, but the error we make with this model became a bit larger than with SOFA modeling. So what can suggest is that for this kind of percentage of soft element into the line, the SOFA became more interesting. And with 40% of soft element, we confirmed that this first idea, because what you can see is the rigid is have more of 5% of error, and the SOFA models give us an error between 0 and 2% in fact. And also the SOFA 1D SOFA beam adapter became very interesting because it's under the 1% of error. And if we go for a full soft line, it's even better for the beam. And at this stage, the rigid modeling has no longer suitable. It has no sense. So it's why we didn't use it. And we can see that the error it's quite manageable and it's quite good. In fact, we are under the % of error. It's almost fit the most accurate mesh from the artist workbench. And another interesting part of what we've done, so we calculate relative error, and what you can see is for 10%, the error is quite the same. It's around 2% for each model. And after the 20% soft elements, we clearly see that SOFA modeling is much more better than rigid modeling, which is quite normal. And also we can see that the beam adapter gives us an error relatively low. And remember, I talk about fast simulation. So another very interesting part for us is the time into the simulation. And what we can see is that ANSYS is very slow. It's because it's static modeling. It's not dynamic like SOFA. And what we can plot also is that the rigid modeling is, of course, very, very fast. It's only, I'd say, basic calculus for computer science. And for the SOFA framework, it's quite rapid, I will say. And also for the 1D beam, which is in the worst case for 100%, it takes only 12 seconds to achieve the modeling, the simulation. So it's quite good. And to see better the positioning of each model, we plot this graph with relative error and execution time. And we can see if we want something very, very fast, we can use rigid modeling, but we know that we are doing an error, a bigger error than with other models. And ANSYS is, of course, giving precise results, but the best compromise seems to be the SOFA one, and also more precisely, I will say the SOFA beam adapter, which give us I think a good compromise between error and execution time. And as a conclusion, I will say depending on the application we are we want to make, if the soft joint is lower than 20% of the total line, and we want something very fast, maybe we will have to go for rigid modeling at the moment. But for any other kind of application, so far with SoftRobot plugin seems to be the best compromise in terms of error and computation time. And we will see in the next presentation given by Benjamin some example of the use of SofaBeam for continuum robots. So that's it for me, and some references. And if you have any question, I'm open.
It's a perfect timing, like to the second close, Maxence. So thanks a lot for the presentation, and as I was writing in the chat, thanks a lot for the Sofa promotion, and actually the comparison with softwares like ANSYS or Abacus is always interesting for us. So it's really good to have that kind of references. Is there any question for Maxence about this study on soft robotics with Sofa? And obviously, I mean, I thanked already Christian for taking the mic, but Christian, you are most welcome to take it again, even if I think you are following what Maxence is doing. Is there any question of the audience? No, wait a bit. Really do not. Yeah. So,
okay. If anyone, I will take the mic if there is no.
I have some, but I'll let you.
How do you plan to use your BIM model in the future? So do you plan to extend it for control and?
Yeah, in fact, for at the moment, as it's a kind of preliminary work about which model to use, but of course, in the future we want to use SofaBeam in order to control, and also the inverse model to really control a robot. And we are maybe in future works we will go for more, I would say, more softer robots. I mean, with a higher percentage of soft element in the line. So we will use Sofa definitely to control robots in the future. And also Benjamin will present some work about with BIM adapter.
Thank you.
And another question is coming from the chat from Stefan, who is asking actually why not comparing, the BIM models of Sofa with the BIM model of ANSYS, and also in terms of performances. I think since BIM models would be also simpler on the ANSYS side, maybe their own performances would be better. So
I will say it's big first. With ANSYS, we cannot do control to follow the question of Christian. So the aim is really to use Sofa at the end for control of robots. So maybe it could be also interesting to compare with a model of BIM in ANSYS, but really the aim of this work is to know the error we made by doing some simplification and show that Sofa is suitable for control of robots of soft robots or soft jointed robots with a low error, I would say.
Thanks a lot. Do not hesitate, Stefan, to add more. So Sergey is asking a second question: what deformation tests were used to compare simulation in both software? Are they used in general case to compare software? So basically, what kind of test scene are you actually using to compare? It seems that you used your bending scene and you run this bending scene in both softwares. Is that correct?
Yeah, in fact, in both software, I will go from the beginning. In both software, in Reactuate, I would say we made a displacement of both the extremity of the structure, and we are looking for the position of the platform. And it was for Sofa, it's a sparse LGL solver, and in ANSYS we have to use it's large deformation part of the software because of the deformation of soft joint. I don't know if I answer well the question.
I would. So basically, did you have an experiment that was actually reproducing that also in real life, so that you were comparing to real data, or
Not yet, not yet.
not yet? Okay.
We have
So
some robots, soft robots at the miniature scale. In fact, the process of fabrication is very hard and long, so we didn't make the comparison with real element yet.
Okay. So yeah, you did answer the question. Sorry, Younes, we're just to avoid going too much. I mean, to be too long for each presentation, we're gonna switch. But please keep this question. So do you try other 1D element like in SOFA for this modeling? I know what is actually the question under the one from Younes. So do not hesitate to ask that directly then in the time for discussion with the speakers right after in the breakout rooms at 10:30. We're going to switch. Thanks a lot, Maxence. We're going to switch to the next presentation, which is related, the one from Benjamin. I'll say that in French, Benjamin. The floor is yours to present. So you work on parallel continuum robots, and from what Maxence said, it's going to be also using beam approaches from SOFA, the one I guess from the beam adapter plugin.
Yes.
Yeah, we see your screen sharing is starting,
Okay.
and yeah, perfect. If you go full screen, should be fine. We've got the presenter here. We've got the presenter view. Can you maybe change the? Yeah, perfect. Yeah, perfect. Thanks a lot. The floor is yours.
Thank you. So hello everyone. My name is Benjamin Mauzé. I'm currently a postdoc in the FemtoST Institute. So as Maxence introduced, I will speak about parallel continuum robots. First, let's speak about more about the context. In Femto, we are working on micro robotics, and in order to perform some application, we need robots that can fulfill the needs of micro positioning, considering the workspace and the precision. Currently, there are two families for industrial robots. The first one is the polyarticulate parallel robots that provide, let's say, a large workspace. So it's millimeter workspace, but it's still large. And some precision, 100 nanometers or micrometers. The precision is limited by the mechanical plate assembling default, and due to the rigidity of such kind of structure, they are difficult to miniaturize. The second family is the flexure hinge compliant parallel robots that use very precise actuation system, and the displacement of this actuation system is very small, and so localized deformation enhance the displacement in order to get let's say a larger space, but it's still very small. So what we want to study is, can continuum structure respond and propose a very alternative to those industrial robots to answer the macro positioning needs. So what is parallel continuum robots? Parallel continuum robots are composed of several flexible continuum elements arranged in parallel that can be individually actuated. They propose, so we can see that there are few mechanical plates because there are also less joints between the actuation system and the platform. The large deformation of the continuum element allow the robot to get a large workspace. And what we can see also is we have the miniaturization capability, as you can see on the picture on the right. So what we want to know is, with parallel continuum robot, the conception, is it possible to get a repeatable robot, an accurate one, in order to get at the end a robot that can perform large workspace, have a high repeatability and high accuracy. Our first proposition was a planar parallel continuum robot, and the purpose of this robot is, if I take using optic fibers as component that can transmit the displacement and the force of the piezoelectric linear actuator to the platform that is above a hair bearing in order to guarantee a planar displacement about plus or minus 5 micrometer. Thanks to this robot, we show that we can perform millimeter workspace, have nanometer repeatability, and a micrometer accuracy. This accuracy has been allowed by the modeling using a Coursera model and thanks to calibration procedure using the pattern on the extremity of the rod. Of course, as Maxence said, to modeling the parallel robot, we are using the actuation pose in order to get the pose of the robot with the direct model, and with the inverse, we can back the actuation pose. Thanks to the modeling, we can get the pose of the robot and we can control it, which is very interesting in order to control the robot in confined environment. But first, we have to define the modeling purpose if we want real-time modeling, or if we can compute the actuator or robot pose previously to send it after that robot or after the computation. And also we want to know how we can modelize the rods and the boundary condition, which is the main component of the modeling. The second application, thanks to Christian Durier from the first team, we work on spatial parallel continuum robots, and we study the fact that we can turn an industrial parallel robot that you can see on the left to a continuum one that you can see on the right. We modelize it with SOFA, and we compare the workspace, the repeatability, and the stiffness of both structure. And we show that we have a better workspace, and we enhance the repeatability by a factor 2. To modelize it, we modelize the forward and the inverse modeling using one mechanical mod, and as Maxence said, we are using the beam adapter plugin and the SoftRobot plugin. And so we are creating 6 rods with 7 elements per rod and 3 double sliding actuators. Thanks to the SOFA, we also work on the more conception analysis using several kind of platform radius, clamping angles, or the rod of the length of the rod. And like this, we can see if we can enhance the workspace and also reduce the size of the robot in order to get better performance. We also identified several singularities for different design of robots, like the star configuration, where we cannot go, we cannot move freely because of the rod will bulk, and also for the over configuration. For example, the middle one, we reduce the workspace in rotation around Z, and for the straight configuration, the displacement around Z. So in conclusion, we show that with parallel continuum robot, we can get millimeter workspace, nanometer repeatability, and micrometer accuracy. We saw that we can create robots that are better than rigid one, and we can use SOFA in order to modelize it, optimize, let's say, the design for the conception, and see the behavior. And as prospects, Christian Durier and Guillaume work on the project in order to create a digital twin of parallel robots using SOFA. Thanks for your attention, and it will be my pleasure to answer your question.
Thanks a lot, Benjamin, for the presentation. Is there any question already for Benjamin? So there have been in the chat some discussion about validation and so on further to Maxence's presentation. Is there any question for Benjamin? I'm going to start directly with one, but please feel free to add some in the chat and so on. Just to understand a bit more, because I was not familiar with your work. It was on slide number 7, I think. The difference. Could you re-explain the difference between your new prototype and the previous? So I understood you increased a lot the workspace, the repeatability, and so on. But it's because some kind of legs here are actually completely are really soft legs. Is that correct? Or
so it's stainless steel legs. So it's not really soft.
Yeah, it's quite stiff. Yeah.
And in order so this result is only about changing the rigid joints into continuum one. What I mean is the platform is it's the same size, and we studied the fact that if we put 2 rods with a larger space at the platform level and very close at the actuation level, we will get exactly the same behavior than the rigid joints for the industrial robots.
Okay, cool, thanks. There is a question. I'm gonna forward you the question, because I think either you have two screens or it's complicated to see the questions. So Adrien is asking a question: did you encounter unexpected singularities preventing from solving the inverse problem, especially when the rods are bent?
Yeah, for example, if we are looking on the configuration on the right, here so far tell us that we lose a degree of freedom, so we cannot get the position of the robot. But let's say it's kind of like we already know that this kind of structure will get a problem, because if we push on the platform, the rod will bulk, and we don't know where the platform will go. So otherwise, no, we don't see. We identified some singularities, so it's what we expect, but no problem, let's say.
Another question from Olivier incoming. Would you expect Adrien is thanking you, and Olivier is asking, would you expect the soft version of the parallel robot to be as durable as the rigid one? And especially regarding the legs, might the legs break after repeated actuations?
Yeah, the fact is, when we don't try to use to see if we can do a lot of cycle with the robot. So we perform some repeatability analysis. So we perform a lot of displacement in order to quantify it. But I don't know if we'll get a better or the same lifetime than the rigid one. What I know is we have to be careful about not reaching the elasticity. We don't want to deform too much the legs. That's why I was quite interesting to know the constraint inside the leg with SoftRobots in order to at the beginning with the simulation know if we can secure the displacement of the robot. I don't know if I answered the question either.
Yeah. Thanking you again, Olivier is thanking you. Any other question for Benjamin? All right. You check out again in the chat. All right. And again, do not hesitate to unmute yourself and directly take the mic for questions here. And again, there will be There is a sorry. So I did indeed miss your here. Yeah, sorry, Eligius. I got actually a warning about the fact that I missed a question, but I did not see it. Eligius is asking, do you need modeling the friction here within the joints, or are you intending it to? No. Okay.
No, because for example, for this robot where the optic fiber are clamped inside aluminum plates, we don't have friction because it's glue. So normally the rods don't move on the platform plate, and as we quantify the repeatability and we get nanometer results, I think if the rod moves inside the plate, we won't get such kind of results. So no, I think we can say that it's rigid between, we don't have friction inside this.
You're muted, Hugo.
Sorry, sorry guys for that. So I just noticed that we were actually a bit ahead from schedule, so I won't stop you. I mean, I won't cut more questions or whatever. Sorry, Maxence, I cut a bit the time. You're gonna have more questions in the break time right after. If there is, for the moment at least, no more question for Benjamin. If there is one last, we can take one last. Otherwise, we're gonna move to the fourth and last presentation of this session on soft robotics, which is the presentation of Michael. Again, anyone can take the mic if needed. Else, I'd like to thank you a lot, Benjamin, for this nice presentation and for keeping the time as well. Michael, are you here? And I'm gonna check here. Yeah, Michael, I see you. Perfect. You seem unmuted. Can you try? Yeah.
Can you hear me?
Yeah, we can hear you. Yeah, perfect. So you should be able to share your screen and share your presentation, so that I'll let you know as soon as we can actually see the slides. Also, in some time, guys, we're gonna, like maybe at the beginning of the break or so on, we're gonna propose some questions that you could actually answer close to the chat. So you might see some questions appearing about your usage of SOFA, some question about the community and so on. Do not hesitate to answer them. So Michael is going to talk about evolving soft robots, which is after self-healing, we're going to have evolving soft robots using fluidic actuators. That's actually it's actually the first time I think we have people using SOFA in South Africa. So that's really cool. Really cool. It's actually you'll see we have a color map on the website and in the slides of the usage of SOFA. You are not yet colored in South Africa, but promise for the next 2022 edition of the SOFA Week, I'm going to update the map so that you do appear among the users and developers of the community. Perfect. We see the presentation. You can, I think, go full screen. Yeah. Okay. It looks like A4 format of presentation, but maybe it's normal. I'll let you change the slides and I'll let you know if.
I think.
Yeah. Perfect. That's perfect. Perfect. Thanks a lot, Michael. The floor is yours.
Sorry, just I mean.
Hey, take your time. No hurry.
Can you still see my presentation?
Yeah, we do. And can you try to switch to the next slide so that we can just check that it's following properly. For the moment, I'm still on the first.
Okay.
I'll let you know as
thank you for everyone having me, and I'm excited to share some of my work. I'm a master's student at the University of Witwatersrand in South Africa, and I am attempting to evolve soft robots with CPPN-NEAT. Yeah, and I've came across SOFA, and it seemed to be a perfect step forward to try and attempt to make evolving soft robots more realistic, and to solve some of the limitations of past research. For a bit of background, neuroevolution refers to the evolution of artificial neural networks. NEAT is an innovative method which evolves both the weights and the structures of a neural network. Some powerful features of NEAT which distinguish it from other methods is that it begins with a simple network structure and slowly adds nodes and more connections to slowly make the structure more complicated and be able more powerful. This ensures that the final network is the optimal size in order to solve the task at hand. Secondly, NEAT tracks all the genes during the evolution. This ensures that during crossover between networks of different sizes and different structures, it ensures that the same genes are crossing over as opposed to swapping genes that are completely different in structure. Lastly, NEAT uses a method called speciation, which allows new structures that may potentially in the future be beneficial, evolve independently from the rest of the population. This ensures that no innovative structures are prematurely ended, and allows them to continue evolving separately. In the field of soft robotics, NEAT has been a dominant method of evolving virtual soft robots by evolving other types of network structures to generate the physical structure of the robots. Currently, one of the most successful results have been obtained by evolving compositional pattern producing networks. CPPNs attempt to generate natural forms seen in nature, such as symmetry and repetition. And CPPNs basically have the exact same structure as an artificial neural network, but instead of using the traditional activation functions, it is allowed to use a whole range of functions such as the Gaussian function, sinusoidal functions, absolute functions, and linear. This allows it to produce the symmetry and repetition seen in nature. Typically, CPPNs receive some input, such as like the coordinates, but it could be anything like temperature, also the distance from the center of the origin, and outputs include things like whether material is present at the coordinate or not, and what type of material it is. Despite lots of progress being made in evolving soft virtual creatures with realistic motions and shapes, there's still a large disparity between the virtual creatures evolved and soft robots that can feasibly be manufactured and used in real-world applications. A major reason behind the disparity is that previous research has made use of less realistic actuation techniques where individual voxels are actuated volumetrically. And this is where SOFA provides a solution, as it has tools to simulate realistic soft robotic actuators, such as like cable-driven actuators and the fluidic elastomer actuator. However, the fluidic elastomer actuator fits CPPN much better than cable-driven actuators, so that is what has been used in this research. Basically, the method that I've been using to evolve soft robots in SOFA is initially the algorithm starts with generates random fully connected CPPNs with random weights and no hidden nodes to start as simple as possible. These CPPNs are then are inputted a grid of coordinates, and where the x, y, and z coordinates, as well as the distance from the center, are inputted into the CPPN, and this provides an output whether there's material at that positioning, and if there is material, then the remainder of the outputs determine which material is at that element. This output is then used to generate mesh files for each part, and then these mesh files are imported into SOFA and connected to form one soft robot. Each soft robot is simulated then for 10 actuation cycles, and the results and characteristics, such as the distance traveled by the soft robot, is used to determine the fitness. NEAT then uses this information to create new CPPNs through selection, crossover, and mutation, and over time, then hopefully the soft robots get better and better, and are able to propagate further forward. The simulation, the evolution that I did, I used a population size of 64, and I ran it for 300 generations. Used parallel computing so that SOFA can run each soft robot at the same time. That way it's not too time, there's lots of time to perform the evolution. The methods and setup in SOFA involves each part is imported into SOFA, like I said. These parts are then attached using attachment constraints. The soft and rigid materials both use hexahedral FEM force fields, whereas the actuating material uses 3 different force fields. One uses a triangular FEM force field, as well as triangular bending stiffness force field. That forms the skin of the actuator. And then lastly, I use a surface pressure force field to actually actuate the actuators. The surface pressure force field is actuated using the SOFA Python 3 controller, and it is actuated in such a way that the volume does not grow approximately more than 20%. Otherwise, you end up with soft robots that are basically just end up being balloons, and the evolution exploits that mechanic. For underwater environments, the evolution or the setup is slightly different. Firstly, in order to create drag on the soft robot, a custom force field was made using SOFA Python 3, and additionally, the mesh of the whole soft robot is imported into SOFA to apply the custom drag force field to it. This also means that then the other parts can be imported as sub-child nodes of the whole robot, and each part is connected to the whole robot using subset mapping. This is some preliminary results of the evolution. We're still doing a lot of runs and tweaking the evolutionary process, as evolution is very good at exploiting any mistakes in the physics, and any exploitation it can find, it does. So yeah. So future work that I will be carrying out is improving the performance by incorporating novelty search first off, and then secondly, using traditional fitness search, but with incorporating domain randomization. The idea behind this is that domain randomization has been very successful in improving reinforcement learning control algorithms by simulating kind of the variability you would expect in the real world. Through this, you would expect that it firstly encourages the diversity similar to novelty search, and also improves the robustness of the results. Additionally, the mesh generation method will be improved by firstly growing the soft the robot from a central element as opposed to inputting a 3D grid. This allows the robot to grow in any direction and is not constrained by the input grid that we start with. Further improvements would also be to instead use tetrahedrons as opposed to hexahedrons. This is just so that more complex and continuous shapes can be used. Yeah, some of my references. Yeah, and thank you for listening.
Thanks a lot, Michael, for the presentation. Very cool presentation. Actually, I'm really no AI expert at all, but yeah, that's something that I did not know, the composition pattern network that you presented. I don't know if some of the people in the audience actually already knew it or are even already using it. Is there any question for Michael regarding this work on soft robotics and cooking actually simulation with AI? That's one of the actually presentation that is and work ongoing, which is doing so. There was actually yesterday a presentation during the Driven workshop on the actually feeding a neural network with a simulation already to learn about how an object is deforming. It was a presentation by Alban Odo, if you want to get for the reference in the program from the Driven workshop. Is there any question in the audience? Yeah, I'm sorry, I did not see you, Andre. Yeah, go ahead.
Yeah, thanks for really. I hope you can hear me. Yeah.
Yeah, we can hear you.
Great, thanks for a really great presentation. I'm involved in the field of soft robotics and evolutionary, and I know these methods, but it's really great work that you have done in SOFA. I have just a short question because I'm interested. The work that you have done have been done in voxel simulators, as you also referenced and showed. I'm just interested, have you compared the results from SOFA and these voxel simulators? Because I don't know, but I presume that SOFA should be more accurate than it has been done in voxel simulators.
We have not compared them, although it would be very interesting and potentially future work could do that. But I mean, one reason for using SOFA was for obviously it was expected that it would be more accurate, but secondly, it was just that in VoxCAD, it's the other individual elements are actuated, whereas like with how I've done it in SOFA, that it forms like a whole bag almost that can be inflated, which is more like an accurate. So I'm actually inputting the actual pressure, which is more realistic in what you could manufacture. But yeah, no, I haven't made any comparisons.
Yeah, thanks. And one more follow-up thing that I presume you would explore, but there is this algorithm called map of elites that you can also nicely try to apply. And this will be really interesting to see in SOFA how it can perform and work.
Yes. I with novelty search, I'll probably also look at other quality diversity algorithms, and that is one that I was looking at. Yeah. Thank you.
Thanks. That's all I have.
Thanks a lot for the two questions in a row. And there have been in the meantime another question, and I was actually having this note on my own notebook. It's actually I don't know if you're aware, but there was a work recently completed by a PhD student on what is called immersed boundary elements, which allows to use exas. Like you're ready to make the FE integration over hexaedra, while taking into account a detailed shape, which is some kind of immersed inside this inside this hexa grid, which allows to both keep the computation on hexa while having a geometry that can be more complicated, like taking into account a triangulated surface. So that was a question from Christian Durier asking open question and linked to the work of the team who worked on this topic, which is the mimesis team. And would you be interested in, or do you think it would be interesting to work on boundary, so immersed boundary elements? Would that be perfect for that kind of optimization?
Yes, I definitely think so. Yeah, so I was not aware of that. But yeah, because that would obviously the hexahedra is a lot faster, which evolution, when you're running evolution, is quite important. So that would be probably great to use. Yeah, because I have run tetrahedron meshes, and yeah, the amount of time it takes extra is just quite a lot in order to get that more detail than you would get from hexahedra. So I definitely think that would be a great option, and I'll look into that.
I was trying to give it to you right now, just like in a few clicks, but I can't find it. Maybe either Stephanie, if you have it. Otherwise, I'm gonna look for it in a few seconds to provide you the link towards this PhD thesis. I mean, it was defended like 4 months ago, so it was something. It's pretty fresh. The code for Hymer's boundary method, so Hymer's boundary elements, is not open yet, and I don't know if it's going to be open soon. But anyway, the collaboration around this work, I think, could be interesting. So in case you want to know more, first, do not hesitate to contact us back, and I'm gonna give you anyway the link towards. So the guy was called Jean-Nicolas, so Jean-Nicolas Brunet. So Mr. Brunet's PhD thesis, I'm going to forward it to you. Is there any other question so far, Michael, in the audience? Oh, Sidati was already faster than everything I could actually dream of. So Sidati already gave you even the page that you could have a look to. So thanks a lot, Sidati. Is there any other question for Michael in the audience? If no, for the moment, because I think at least I have some others on voxel-based simulation. Maybe I remember about some discussion topics about that with Damien Marchal. So I think that could be interesting to get voxel-based simulation in SOFA. There was so I noticed as well the tetrahexa for Hymer's boundary methods, and maybe we could also exchange a few words about a project which is ongoing. 2 projects are actually ongoing, coupling SOFA and AI to get Python-based platforms. So instead of everyone developing his own platform to couple simulation and AI, there is actually 2 projects coupling. First one is for OpenAI, and another one is actually aiming at making something very generic for coupling SOFA and AI platforms. So this is definitely something I'm gonna join you in the breakout room so that I can. We can chat about that in a few minutes. Okay.
Thank you. That would be great.
So thanks a lot for the questions here. So yeah, the layout will be given for the breakout room. I'm gonna just share my screen so that you can actually see here. You can actually see there you are. You should be able to see my screen again. So that was the plan. I mean, that was the session for SoftRobotics. We had the presentation of Pasquale first on self-healing robots, Maxence, Benjamin from Femto-ST on parallel continuum robots from Benjamin, and finally evolving SoftRobots using AI from Michael. We're going to create actually associated subrooms that are actually called here breakout rooms or sessions scindées in the French version that I have here. But we're going to create specific rooms. They're still going to be the main room that you can stay there, but we're going to create subrooms. You can join the speakers, ask all the questions you want, and at the end of the 20 minutes, so it's going to be 20 minutes of breakout rooms, the rooms will automatically close, and we're going to get back to the main room. So do not hesitate to just join one of those rooms, join the speakers, ask as many questions as you want, and we are going to join again in the main room at 10:50 CET, so it's going to be in exactly 20 minutes. Guillaume, are you ready for the splitting of the rooms?
Yep. Yep.
Perfect, thanks.
I'm doing it.
All right, so you're all going to see a proposal to join some rooms. So it's a good point. I think we've got someone yesterday, Hadi, that was actually just updating like F5, and when he connected again, I don't know why he needed to connect twice, and at the second time, the English was actually by default in English. So sorry about this by default French stuff. Frenchies are always comfortable with staying just in French. Sorry about that. So again, room 1, Pasquale, room 2, Maxence, room 3, Benjamin, and room 4, Michael. So do not hesitate to join the speakers. You'll have the proposal in a few seconds.
Okay, the rooms are created. You should see them somewhere on your screen. The 4 presenters have been automatically dispatched to each room.
And any one of you can actually join. Yeah, I see the first people are already joining here, Pasquale, for questions. So you can just click on for me, it's actually the 4th button called Sessions Scindées in French, but it will be breakout rooms in English. So if you click there, yeah.
Nothing appears on my side.
No, on the 4th, if you click on the 4th button down here on the interface.
Yeah, you have to click yourself.
Yeah.
There is no
I thought
pop-up.
there was good. Yeah, there is no pop-up, yeah. So yeah, people start joining. Let us know if you cannot join the rooms properly, or if you do not know where to actually click to join. Yeah.
Hugo, can you maybe just let the slide you just showed before with the 4 rooms?
Okay. So I can share again.
Yeah.
There you are.
Cool.
Yeah, and as Alexandre and yeah, so and Frederic also are saying you can directly find another button if you click on the participant list. You have all the list of the participants. On the top you have the main meeting room, and on the right you have just below the number of participants on the top of the list, participants number 83, and you have main room, and then you have breakout rooms or session scindée, and you can just join the people you'd like. Okay. Thanks a lot. Guillaume, can I join one of the room? Maybe it will. I'm gonna lose the sharing of the screen. Maybe.
Okay.
Okay. Could you do it? Maybe sharing the.
I can, yes. Oh, you're leaving because there is the ask for help from Sadati?
No, it's. I'm gonna reconnect. I have a wait window on my end,
Okay.
so I'm gonna just
Okay.
try to reconnect.
Go ahead.
Okay. Can you hear me again?
Yes.
Can you hear me back? Perfect. Okay, I got a wait window here. Okay, I'll let you sharing the slide. It's slide number 21 of the SOFA Week presentation. Maybe you can also drop a sondage. I don't know how to say a sondage in English. Okay. Look for that.
A poll.
A poll. Thanks. Okay, I'm gonna go in some breakout rooms. Session test. Right. Is that fine for everyone, the transition within the breakout rooms and so on, or is there some people here who are maybe stuck or whatever? Do not hesitate to unmute if you have any issue, but I guess from what I see from the chat, Fred and Guillaume already supported you here. And welcome back. Everyone should be now automatically redirected to the main room. You can, so just so that you know, we are sometimes, deactivating cameras of people. It's also for, as we said at the beginning of the symposium, it's also for the bandwidth of everyone. So sometimes, depending on the connection of the speaker, especially, can be a bit the sound can be a bit cut and so on. So that's why. Guillaume, may I present? I mean, not take the presenter, but just share my screen again. Shall I?
Yep.
All right. So. Okay, but so just I'm okay. There is currently a poll that you might have noticed, so do not hesitate. Okay, it has been closed, but there was a poll, so we're gonna restart polls regularly. If you want to reply to those polls, please feel free. I mean, it's a way for us to know what you think about SOFA, about your usage of SOFA, and so on. And so for us, it's quite interesting to get some feedback from the whole community, whether you are just curious about SOFA, using SOFA, a developer of SOFA, a god of SOFA, whoever you are, you can actually contribute and give us some feedback about the project. It's always cool. So we'll move to the second session of the day and the second and last of the morning for us in Europe, but afternoon for some others, and very beginning of the day for some others in America, which is namely the numerical method session. So numerical methods for simulation. And namely, we're going to have four different presenters and speakers. So the first one, which is from a company that you might know now, which is called Insimo, a company working on medical simulation and providing highly realistic simulators, also online simulators. You could discover everything online. So Philippe will present his work on the implementation of a new linear solver using left Cholesky decomposition. I told you it's going to be numerical methods. It's going to be real numerical methods. Then Arnaud, and I already teased a bit to some of you the work of Arnaud, coupling SOFA and FeniCSX, how to use the automatic differentiation potential of, feature of FeniCSX into SOFA. Ziqiu will present his work on I would say, improving the compliance matrix computation, making it faster, especially for the case of contact simulation. And finally, Guillaume will present his work on adjoint method for surface matching. So it's going to be a simulation-based registration and using Python 3. So thanks again for the speakers for applying to the today's session for presentation. Thanks again for being so numerous in the breakout rooms for asking questions. Let's get started with the numerical methods. Philippe, I can see that you're already online on stage, ready to start. You can actually start sharing your screen if you.
Yeah. Hello. Can you hear me?
Perfect. Clear.
Yes.
Cool.
Okay.
So you can share your screen, share your presentation. So is it? I think it's even more, a bit more, but the result from an internship, right, Philippe? And now the result of your ongoing work at Insimo.
Yeah.
I'll let you giving us the context and the floor is yours. Can you maybe put it full screen, and then it will be perfect. Great, perfect. Thanks.
Okay. So hello everyone. I will present you my work that I started by an internship with Insimo and Mimesis. So it started in March, and it is about studying the possibilities to use updates to compute updates of Cholesky factorization, and so to implement a new linear solver using that updates. So I will present you my research topic, and after I will talk about Cholesky factorization, and I will show you my first results and the work in progress. So what I work on this weeks and the next weeks. So the first work was to study the possibility of updating a Cholesky factorization. So it exists several implementation of Cholesky, and the idea was to first was to study one implementation that is adapted to use updates. And so after it was the objective was to implement a finite element method that allow us to use that updates. And after it's after the first test and the first studies, I implemented the beginning of a new linear solver using this partial Cholesky factorization. And of course, we are studying the stability and the performances using this method. So just to recall, the system resolution process that we are interested on is to, when we discretize the temporal evolution of a system by small time steps, after we, so we discretize the system, the dynamic equation, and we construct a global matrix that we will factorize using Cholesky. So of course, the system is positive, definite positive and symmetric. And so we are applying Cholesky factorization at each time step. And so the idea is to use not compute entire factorization at each time step, but the idea is to update this factorization. So just a recall of what is Cholesky factorization. So if you have a positive definite symmetric matrix, you can write it as a triangular matrix L multiplied by its transpose. And so it exists several implementations. So at Insimo, we are using up-looking factorization. And during my internship, I was studying, and I am still studying left-looking factorization and also up-looking factorization. So I started to study left-looking factorization because in the literature is more adapted to compute updates. So the phase of factorization is we have an ordering, so we find a permutation to reduce the fill-in, and after we have a symbolic analysis. So we first build the sparse structure of the factorization L and the elimination tree. And after we compute the numerical factorization. And the idea in using updates is just to repeat numerical factorization and not only fully numerical factorization, but just a numerical factorization of just some columns of the factorization. So the special features of left looking is that we are computing a more expensive symbolic analysis, but after we will win a lot of times using just partial numerical factorization. So just to show you when we have just an example. So first we have matrix, we compute the permutation to reduce the fill-in. The fill-in is to reduce the number of values in the factorization, because if we have less values to compute, we are faster. So after I show you the sparse structure of the factorization and the elimination tree. The elimination tree gives us dependencies between columns, because when we compute a column, we have to calculate. It depends on others columns. So we use permutation because we reduce fill-in, so the number of values, and we obtain also an elimination tree that is less that have many branches, so the dependencies between columns is attenuate. And when we have the structure, we compute numerical factorization, and you can see if we have a good sparsity, we have less values, and it goes faster. So when we update a factorization, so here in my example, I change two values. So we first compute we first find the columns that change in the system matrix A. So here it's 5 and 8. And after, we use elimination tree to find all of the columns that have to be updated in the factorization. So as 5 as for parent 6 and his ancestors are 7 and 8, we go up in the elimination tree to find all of the columns that we have to update in L. And after that, we can compute the numerical partial factorization. And so to take updates of the system matrix A, so we use a finite element method that is called warp cancelling corrotation. So it is a combination of a corrotational method and stiffness warping method that we compute a combinations of nodal rotation matrices and element matrices to obtain an approximation of a force applied on each element, and we compare it with the correct, the exact force applied on each element, and we compute the error. And if the error is too large, so we update elements. So to show you the results, so the stability of the method, I have a video. So I have to leave full screens. Okay. So here we have 3 torus. So on the right, we update all of the elements. So we compute entire, we update all the elements. On the middle, we update the elements that need to be updated using warp cancelling corrotation. And here on the left, we update nothing. So here we can see in red and yellow the elements that have to be updated. So here is the first idea to see what it looks like. Okay, and so about the performances using SOFA. So last weeks I was implementing the full algorithm on SOFA because I first implemented on the language C to just study and test it. And so we are interested first. So it's not about updates, but just full factorization. So the idea is to see if we have approximately the same time in computing fully into full factorization between the uplooking that we already use in SOFA in SIMO and the left looking. So he BSC for block sparse columns because we use blocks of 3 columns to compute it. And so on these 2 examples, we can observe that we have differences, but it's approximately the same. So if it's the performances on the full factorization is the same, we can hope that using updates we will earn a lot of time. And here, last graph I show you is the just the first graphic of the performance. It's a quick overview because it's in the language C. It's not really optimized, and it is on a big matrix. But it's to show you that we can hope that when we do a small percentage of updates in the matrix, we can hope that we earn a lot of times. But after a certain percentage of updates, it will be not worth to use updates, and it could be better to compute a full factorization. Just to end the presentation, I'm still working on use partial factorization with a linear solver, because I just implemented the full factorization and the updates, but I'm currently not using partial updates on the scenes. I'm just using the finite element method, applying the updates of A, but I'm still computing fully factorization of this approximation of the system matrix. So my next work will to use this partial factorization, and to also to test if I can still organize better the structure of the mesh to update by partition and not to update if it's not really organized, because when I show you on just the video, we observe that it is not really well organized, and the elements are updated in every zones in the torus. And finally, I will also will implement the finite element method on other types of elements, because I just tested on tetrahedrons. Thank you for your listening. Sorry if it was quick, and if you have question, you're welcome.
So sorry, the format is quite short, and
yeah, sorry.
There's actually and it makes always easy to actually overpass the time, but no problem. Thanks a lot for the presentation, Philippe. There is actually a first question coming from Adrien saying,
yeah,
you said slide 12 that you did not update the factorization, but the behavior seems identical to the other simulations. Shouldn't the simulation be unstable in this case? So I guess he's referring to the left-hand side.
Yeah, on the left torus. If we are moving the tor, it explodes. So it is totally normal, because we update nothing, and it's always when we are at the time step 100, it is it's still the system matrix at time step 0. But yeah, it's quite strange. If we don't move it, it
remains relatively stable.
Yeah.
Thanks. And never hesitate to share those kind of very nice, I would say, unstable and even unconverged artistic image. It's always cool to see that. Thanks a lot, Adrien, for the remark. And there is another from Sergey. I think we're gonna keep that, because we are already 5 minutes late here for the next session. Sergey, keep your question. I've got also 3 on my own, so I'm gonna join you in the room later on. Philippe, thanks a lot again for the presentation. We'll move on to the next one. So the second one, we're gonna again have 4 different sessions before the break and the discussion time. So next session is the one from Arnaud and I teased already several people, and so I've learned also the latest updates from Arnaud recently. So you're gonna learn about the coupling of SOFA and Phoenix, and how to use automatic differentiation to use directly that kind of codes in your FE SOFA simulation for hyperelastic simulations. So thanks again, Philippe. The floor is yours, Arnaud, and for questions, keep them warm, and we'll take them at the break time at 11:50.
Hi everyone. Can anyone hear me and see the presentation?
Both. Perfect.
Nice. Okay, so thanks for letting me talk. So I'm Arnaud Mazier. I'm a PhD student at the University of Luxembourg. And we recently started to work with Jean-Nicolas Brunet, which is now a doctor in INRIA. So the idea was to couple the Phoenix software, which is mainly used here in Luxembourg with Jack Hale, and to couple it with SOFA to take advantage of the automatic differentiation provided by Phoenix to be used in hyperelastic simulations. So one of the motivation is that, for example, when you use Saint-Venant-Kirchhoff law, it's quite easy to obtain some derivative of this law because the dependency is quite nonlinear. I mean, it's not so nonlinear. But when you move to more complicated law like anisotropic Ogden models, it gets way more tricky, and we could take advantage of automatic differentiation for this. So the outline, quickly I will introduce you the Phoenix project and what are the key features which could be relevant for SOFA. After I will show you one of the latest application we had and what are the next step of development. So first, the Phoenix project, if you want to take a look at the project, I let you the URL. So it's a computing platform for translating scientific models into finite element simulations. So it's a fully open source with almost 15 years of using now. So it's made to rapidly prototyping and testing novel finite element methods, but also numerical solvers and different scientific hypotheses. It's a really nice tool for teaching finite element method to students, and it's also allowed to write robust, scalable, and maintainable finite element solvers in the context of large software project. So it's mainly designed for users who already know what is the finite element method and have a good notion of partial differential equations and also need knowledge about the problem you're trying to solve. So to test it, it's super easy. It's already on Docker, for example, and you can contribute also to the project on GitHub. So the different key features, how does Phoenix work? So usually you have, good. Usually you input some UFL language to describe your problem. So it's also like SOFA as a Python wrapping with C++ underneath. So you write your code in UFL language, then it is translated with the FFCX to transform it into C code. And then the C code is read by Dolphinx, which also use a Python interface to orchestrate and execute the simulation. So like I said, in the UFL, you can write the mathematics as code. So for example, something that you will write on a piece of paper, mathematic formulation, when you have this bilinear form, you can easily describe it with the UFL language, saying that you have an inner product between the gradient of U and the gradient of V. U is the trial function which belongs to the V space, and the V should be the test function belonging to V space also. So it's just a way to really easily getting from paper to code. So after, a second nice feature is the automatic differentiation, because it allows to remove tedious and error-prone manual differentiation steps, and also it operates at the variational level like Ajax, or which is used in TensorFlow, if I don't misunderstood. So in the context of hyperelasticity, we usually have a strain energy to integrate. And what is nice is that you can derivate it to obtain, so usually the residual vector and also after the stiffness matrix. So those sometimes painful derivation can be easily done in one line in Phoenix by using the derivative keyword, saying that you want to derivate this energy about U in the direction of V. So it's really easy to do. And after we pass to the automatic code generation using FFCX. So once you have written your file, you just run FFCX your file, and you obtain a really large piece of C code where you can have your functions which are integrating your functions over the domain. So here, for example, it's just the beginning of the function. But so you just give the matrix where you want to store the result. You can give also some weight, some constants. So it's mainly about the Poisson ratio and the Young modulus in the case of elasticity problems. And after, usually, so it's read by Dolphinx, and it's where I was working on replacing Dolphinx by SOFA. And so in the context of SOFA, how usually it's done, so you have a force field. So we mainly worked on Jean-Nicolas, which has done a lot of work in the force field to make them more easy to understand on a mechanical point of view and also more efficient. But in those files, usually you have two functions, so the add force and the add k to matrix, which allows to assemble the residual vector and the stiffness matrix. And usually how it works, so you loop over the elements, you loop over the Gauss nodes, and on the Gauss nodes, you will construct your first Piola-Kirchhoff and the compliance matrix. You will use them to build the residual vector and the stiffness matrix locally for each element, and after you will assemble the whole. What we're doing now with Phoenix is that we are looping over the elements, but instead of going into the Gauss nodes, we directly use those functions that we generated with C code, which already is embedded inside with the shape functions and the kind of elements and all the operations that are necessary to build the residual and the matrix, the stiffness matrix. So like I said, we don't need now to build the S and C matrix and no need to calculate the shape functions. And we made a slight economy of 60 lines for the moment. So the first application was to use it on a beam case with a Saint-Venant-Kirchhoff material. We fixed the left side and we applied the pressure on the top with 5,100 degrees of freedom, and it's a tetrahedron of order 1. So the first result is that so we run both the SOFA code and the SOFA with the Phoenix part. So what we see is that in a 6 Newton iteration, the residual norm is the same, aside at the last step, but the difference is really few. I didn't display for SOFA X Phoenix also the norm of the displacement increment because it's exactly the same. And for the time, there are some slight difference, but it's kind of reasonable. And also, I didn't really optimize the import of the C code. So maybe we can work on this to maybe do this 20 millisecond left. So in the summary, to sum up, so we write and use the automatic differentiation. So for a Saint-Venant-Kirchhoff model on a P1 tetrahedron, we generated the C code to create the local stiffness matrix and the residual vector. And then we read the C code into a force field in SOFA to build the global stiffness matrix and the global residual vector. The further development is to use more complex mechanical laws, such as the Hozapfel-Ogden anisotropic model or any more complicated model, and also to use more complex element with higher interpolation degree, such as hexahedron of order 2, which can be useful for incompressibility. And also we need to think about how to use SOFA features that could benefit also Phoenix project, because Phoenix project is mainly designed for mathematical problem, but maybe they also can use some contact features from SOFA or something we can think about. We can look also on more complex mechanical problem, or also any other application than something different from mechanics. If someone has any idea, we are really open to discuss on those matters. And thank you for attention. And if you have any question, please be free to ask me.
Thanks a lot for this very in-time, clear, and nice presentation, Arnaud. You've got already congratulations from Stefan saying, "Oh, great and very clear slides." There is a point from Olivier rising. So would that allow to have Newton iterations in SOFA? In fact, using I think you used the Caribou plugin. Is that correct, Arnaud?
For the moment, it's not relying on Caribou plugin. It's just a plugin that Jean made the side. So it really looks like the implementation of Caribou.
Okay. All right. Thanks. So just so that you know, Olivier, in some plugins, there is actually, so first in SOFA for the static solver, you have a Newton iterations possible. And then in other plugins, open source plugins like the Caribou ones, you do have also some Newton iteration solvers existing. Solvers integrating Newton iterations. Is there any question? I see already Stefan unmuted, so go ahead, Stefan.
Yeah, thank you, Hugo. Great work, Arnaud. Very cool stuff. And so I was wondering, like, for the first point you have on your slide, actually here, I mean, aside of Phoenix struggling with more complex elastic laws. I mean, do you expect any additional issue when using, I don't know, like Ogden, for instance?
As far as I know, for the moment, I don't really expect any issues.
Yeah.
So the automatic differentiation should do the job, and the assembly should be really similar of what we did in the force field. So it should be okay.
Yeah, that's what I was thinking as well. But okay, and for the higher order elements, because this is something that I think is a little bit maybe trickier, because if you choose to, I would say, integrate and let's say hexahedral element of order 3 in Phoenix, the same element should exist in SOFA, right? This is maybe the only limitation so far, something like that.
So for the moment, I didn't try in Phoenix. I think it should also do the job because I already tried a tetrahedron with a higher interpolation degree, and the C code was normally generated. But after, yeah, I have to think of how to deal with the change of elements. I think hexahedron are already embedded in the Phoenix. It should be able to do it, but I'm wondering how I can integrate it in SOFA. But I think maybe Jean-Nicolas already did some work on hexahedron.
I think he did, but maybe I will rephrase my question. I guess my question is more like, let's say you want to, for an application, use Ogden on an hexahedral mesh with elements of order 2. Do we need to have an implementation of hexahedron elements of order 2 in SOFA or not?
Yeah, I mean, yes, we will need it. Just because the fact that we change the material law doesn't really change what the force field, but the change of elements, yeah, the force field should have more degrees of freedom to take this change of elements into account.
That's what I was thinking. Okay, that's clear. Well, I'm super excited about this, and I hope we can discuss more during the rest of the week, because I think this is really opening lots of interesting options for more complex models in SOFA. So thanks again.
Thank you for your question.
Thanks, Arnaud. So there's additional questions. I think we're going to keep them for the breakout session. There's a question from Eligius, from François about the boundary conditions. There was also the question of, is it open source? So maybe this can be a yes or no for Christian. So
yes, it is open source. For the moment, I just have to work a bit on the GitHub because I just set up a few workflows, but no test for the moment. But yeah, it's already set up.
Okay.
And
so
it's
and for the
first, it's on the first slide. If you.
Thanks a lot. Yeah, maybe if you can copy paste it after your presentation in the chat so that people can take a look. Thanks a lot, Arnaud. And for the questions, so François, Eligius, and I have again some others, and I guess others who also have some questions. I was thinking about Pasquale as well, who is working. We saw the self-healing SoftRobot. I think it could be interesting to implement this self-healing law within Phoenix and getting automatically the code generated, derived and generated as you're doing. So yeah, thanks a lot for the presentation, very clear. And let's see in the breakout room for questions. I also some points about GPU computing. We'll see that later on. Next presenter is Ziqiu from INRIA and eCube Laboratory. So Ziqiu is working on the fast computation of compliance matrix in contact simulation. You'll see it's very related to the first nice presentation of Philippe, who was working on matrix assembly and matrix factorization. Here it will be how to assemble and compute the compliance matrix in an efficient way. So it's still some matrix analysis and optimization. Ziqiu, you already teased us last year with your first presentation. Let us know about your latest updates on those isolating mechanical degrees of freedom.
Thank you. Could you hear me? And
yeah, perfect.
I'm now ready for the sharing.
Seems to start.
Okay.
And it works perfectly. Yeah.
It works. Okay. let's start. And hello everyone. I'm a PhD student in the team Mazier area and iCube laboratory. And today I'm glad to share you our new methods to compute the compliance matrix in contact simulations. And firstly, insofar to realize a contact simulation, we usually use constraint-based approach to solve the problem. As we can see, we have several steps to process. And here we can see there is a process short complement to build a compliance matrix, also called the Delass's operator. Sorry for that. And this matrix W is built to couple the constraints. But building such a matrix is usually very costly in large scale simulations, because A is usually very large and very hard to be inverted, and H has multiple right-hand side. So makes the computation very costly. And then so far we have a solution. An important technique is the asynchronous preconditioner. We use an asynchronous thread to build an LDL to factorize the system, and we use the result of factorized system as an approximation of the current system matrix, and this helps us to remove the costly factorization process out of the main simulation loop. And even with this asynchronous scheme, and even the building stage of W in main simulation loop is well parallelized on GPU. There are still some operations that remain very costly. Here, an approach is to build the W with a two-step method. The first one is a sparse triangular system, which can be very costly because it's on GPU, because it's hard to parallelize. And the second one is matrix multiplication. This one is usually very efficient on GPU because it's easy to parallelize. And then for the computation time, we observed that even for large-scale simulations, even with good parallelization on GPU, the short complement is still very costly. It takes about almost 80% of the whole time step. So accelerating this step is necessary for real-time applications. And for the now to improve this stage, we propose two methods to faster compute the compliance matrix. And the first one, we name it as isolating mechanical DOFs, and the second one is developed from the first one. We call it as reuse ISODOF. And let's first consider an example. A deformable raptor mesh is contacting with a rigid plane, and we can see that the contact zone is located in some area, and this makes the constraint Jacobian matrix very sparse, because only a part of mechanical DOFs are impacted by the constraints. And following this observation, we propose to reformulate the short complement. Firstly, we separate some information in Jacobian matrix. Here, we firstly eliminate all the empty rows in H and formulate a compressed matrix H hat. And then by choosing the non-zero columns in H, we can build a partial identity matrix IR here. and the relationship between the matrix can be actually expressed as a matrix multiplication. And here we have some essential properties for this matrix I bar. It has one and only one element on each column, and each element has no value information. The values are all set as value 1. So now with this reformulation, we have generated a new dimension which we call the isolated DOF dimension, which are actually the DOFs impacted by the constraints. And so with now with the reformulation with this matrix multiplication, we can reformulate our original operations to build the compliance matrix. Here we replace the Jacobian matrix H by the multiplication. Then we will have a new formulation, and to realize this this process, we have a 3-step algorithm to finally build the W. The first one is still sparse triangular system, and using a traditional triangular solver will be still costly. And the second one and third one are just matrix multiplications, which are efficient on GPU. And then let's focus on the first one, which is a triangular system resolution. We have special right-hand side. For each right-hand side, we only process the necessary data, and this is according to the data dependency in the triangular system. So the resolution is very sparse and very efficient because only a few data are processed. And then this resolution makes the first step very efficient. Then, given the properties in the isolating mechanical DOF method, I would like to introduce our second method, which named as reuse ISO-DOF. We find that consecutive time steps usually shares many ISO-DOF, the DOFs impacted by the constraints. So we can recycle the result in consecutive time steps, and we can benefit further speed up from it. And now let's look at some simulation results. And for the isolating mechanical DOFs, by processing the sparse resolution, we compare to the dense resolution, which is currently the fastest GPU implementation in so far, and we have gained significant speed up. Then, by reusing the isolated mechanical DOFs, we have a further speed up compared to the standard isolating DOFs. And then another point very important is that from the dense process to the isolating DOFs and finally to the reuse ISO-DOF, we have exactly the same accuracy. We have processed the same computation in the process, and the only approximation we'll have for all the methods is using the asynchronous preconditioner as an approximation to the system matrix. And now we compare the different methods in a very large scale simulation, which has 60,000 DOFs and 2,000 constraints. We have the first the media paper, which was the fastest implementation insofar, but it remains very costly to build the compliance matrix. And now with our it was very costly, and now with our new method, this is significantly improved. And now we have a very we only to the short complement only takes 8% of the whole time step, and we have nothing changed for other steps. Okay, and then I would like to share you some interesting examples for using our method. And first scenario with large dimension, we can compare different methods, and we can observe an obvious speed up using our new method ISODOF and reuse ISODOF, and the building W can be very efficient in the simulation. And then we have we try to meet different challenges in various scenarios as a complex interaction, multi-objects, and heterogeneous material. And for all these scenarios, our method has an efficient performance. And finally, we also simulated an interesting grasping task using the SoftRobots, and this can be also very efficient with large dimension of mechanical DOFs and contact constraints. And thank you for your attention. And I would like to know if there are some questions.
Thanks a lot, Ziqiu, for the very nice presentation and trashing the Raptor at the end in your demo. Is there any question for Ziqiu in the audience? I would guess maybe some questions, maybe from Alex, Christian. Yeah, sorry, Ziqiu. What?
I've stopped my presentation.
Yeah, no problem. If you want, you can restart it.
Okay.
So, is there any question here for Ziqiu regarding his work on isolating DOF for building the compliance matrix? For those who are not maybe used to, I don't know, solving constraints and so far, I put a link above in the chat if you want to have a bit more info about the constraints in so far. More generally, what actually Ziqiu is showing here is super generic, meaning that as soon as you have constraints, collision that will be solved using the Lagrange multiplier approach, this kind of method, this isolated DOF method, will be applicable. So there's quite a lot of potential here. Sergey is asking, does your approach work for non-linear models, like non-linear constitutive laws?
Actually, the nonlinear method is completely compatible. Our method is ISODOF method, and the reuse ISODOF method is compatible with the non-linear method models such as hyperelastic models, because we will always assemble and system matrix, and this is just to exploit the sparsity in the matrix. So it's totally compatible. But in our scenarios, we only tested with correlational models, because now the hyperelastic model in SOFA, we have a very costly computation in the when building the system matrix, so that will disable the real-time application. So that's the only reason we're not yet tested with a hyperelastic model.
Thanks a lot, Ziqiu. Is there? Yeah, I was awaiting François to take a question. Again, I'm speaking for you guys, but do not hesitate to unmute. I always prefer to hear your sweet and nice voices wherever you're located. So, just to make the transition for François, a remark maybe on the CPU. It is the sparse triangular solve. The triangle is not the dominant phase during the computation of the short complement. Yes, it's just a remark, I think, from François.
Yeah. We also in fact here we also compared with the partition with which is a CPU resolution. In fact, how to say, in CPU it's not maybe not the case, but in CPU the matrix multiplication can be very costly, and how to say, on GPU we can it was costly for the triangular system, but now with our method we are this is no more the obstacle. So so how to say, I may insist that now our method is even better than the powerful servers on CPU. And
thanks a lot, Ziqiu. Anyway, since we're running a bit out of time, I will keep further questions for the breakout room, which is after the next presentation, after Guillaume's presentation. Thanks a lot again, Ziqiu. And so you can meet Philippe in room 1, Arnaud in room 2, and Ziqiu in room 3. And there will be Guillaume in room 4 after Guillaume's presentation. So Guillaume, are you around here? Are you available? I'm going to check. Yeah,
hi, do you hear me?
Perfectly fine. Can you try sharing your screen as well?
Yeah. 1 minute.
Ziqiu, I'm shutting down your mic.
Do you see
and
my
your camera.
screen?
Not for the moment.
Okay.
I'll let you know as soon as the sharing will start. Okay. So we are having like small, less than 10 minutes delay. Start anytime you want. Guillaume, we're sharing the screen. Go ahead. So we are having about 10 minutes delay. So around noon there will be the breakout room, and there will be time for asking questions to Philippe, Arnaud, Ziqiu, and Guillaume.
I cannot share my screen.
Using the button down here? Yeah.
I will try with another.
Another browser. Okay, go ahead.
If I have one.
Yeah, definitely for the speakers. Maybe for the speakers of this afternoon. I mean, it's always preferred to use Chrome or Chromium or similar to actually work on the platform. So it appears to be a bit more stable. I hope the experience of the stream experience is good for everyone wherever you are located.
I'm sorry for the delay.
Yeah, no problem. Go ahead. In the meantime, what I can propose is, so I'm just gonna speak for a few seconds. Go ahead, Guillaume. There is indeed a standard. There is a WebEx application if needed for those who want. But more importantly, if you want to vote for the best contribution, I give you again the link to vote. You can only vote once. I would ask you avoiding trying to cheat and inviting your relatives and family to vote. But that's where you can actually vote for your favorite contribution for the SOFA Awards. Again, at the end of the symposium, in a few hours, we're going to give first the organization prize and also the public prize that you guys are the one to elect. I was not involved neither in the public or in the organizer prize. So please feel free to vote. And next year, again, any contribution is welcome. I'm going to get back to that right after lunch, but any presentation is most welcome. So never hesitate to contribute. Welcome back, Guillaume.
I'm trying to...
We can still hear you.
I don't understand why it's...
What's your point, Fred? I see Fred is asking a question. I mean, repeating the question of Sergey. Okay. Well. Can you see the button now, Guillaume?
It's a question of authorization for Chrome to. I'm on a Mac and I didn't expect. I'm not used to this.
And just wait for let's wait for another minute if you can try to set that up, and otherwise we'll have to perfect, it's start working.
Okay, yeah, you see my screen
perfectly, okay. And we can hear you. Go
Sorry
ahead.
for the delay.
No problem.
Hi everyone, my name is Guillaume Mestdagh, and I'm a PhD student in the Mimesis team and also in the University of Strasbourg. I will tell you about my implementation of an adjoint method for surface matching with SOFA Python 3. The goal of this presentation is to see how to run an adjoint method and do optimal control in SOFA without writing a line of C++. So first, I will tell a word about the optimal control I'm interested in. Then I will go a bit into technical details to see how we do that in SOFA Python 3. And finally, I will show, if I have time, I will show an example in relation with augmented surgery. So the problem I'm interested in is a surface matching problem. It's simple. We have an initial volume mesh. We have a point cloud that represents the surface of the mesh in a deformed configuration, and we want to find an elastic deformation of the mesh, so that the boundary of the deformed mesh matches the point cloud. We want this deformation to be elastic, so we have also an hyperelastic model for the solid. We add an additional hypothesis on the deformation of the displacement field we want to compute. It should be created only by applying forces on the boundary of our solid. So here on the right is the equation of the direct problem. So we compute the displacement field U from the surface loading G by solving a nonlinear hyperelastic problem where the hyperelastic model is stored into the function f. To perform the registration, we solve an optimization problem. So in this problem, we minimize a cost function, which is j. But you can see that this function is a function of u, of the displacement, while our optimization variable, the variable we control with the optimization solver, is the surface loading. So if we want to evaluate the cost function, we first need to solve the direct problem, the nonlinear problem, to compute the displacement and then evaluate the cost function. Okay, but now we want to solve this optimization problem with a gradient-based optimization method, like a gradient descent or a quasi-Newton method. So we also need to differentiate the cost function with respect to the optimization variable, that is the surface loading. So this is the role of the adjoint problem, of the adjoint method. So to differentiate the cost function with respect to the control, to the surface loading, we have to solve, to introduce an adjoint state, P, which is a solution of a linear problem involving the gradient of the cost function with respect to the displacement and the tangent matrix of the system computed at U. So this is the same matrix we inverse when we compute some Newton iterations, right? And we can show that this adjoint state, P, is actually the derivative we are looking for, the differential of the derivative of the cost function with respect to G. So let's on the right have a look at the full pipeline. The optimization solver is required wants us to evaluate the cost function for control G. We first solve the direct problem to find the displacement. Then, using this displacement field U, we evaluate the cost function and its gradient with respect to the displacement. Then we solve the adjoint problem to compute the adjoint state P, and we can return the value of the objective function and the gradient, which is here P, to the optimization solver. Now, before we see how we do it in SOFA Python 3, just have a short look at the scene. We have an hyperelastic force field from the Caribou plugin, which is used to define the elastic model and assemble the tangent matrix. We use a constant force field in which we will set the forces before running a static elastic computation, and also a mechanical object in which we will read the displacement field after solving the direct problem. Here, the solver is a static ODE solver. It's not we are not time dependent. It's static problem. So this solver is basically a Newton method. Let's have a look at the pipeline. So we only need SOFA in two steps. First, solve the direct nonlinear problem, the elasticity nonlinear problem, and also to solve the adjoint problem. To solve the direct problem, it is business as usual for SOFA, right? We just can use SOFA as a black box. So we use the function sofa.simulation.animate to perform the direct simulation. To solve the adjoint problem, it's a little more tricky. We will do it partly in SOFA and partly in Python. So we can use the nice new bindings prepared by Jean-Nicolas Brunet in his Caribou plugin. We assemble the stiffness matrix at the displacement field we found using the function assemble stiffness. And we can grab this matrix from SOFA to Python using the binding K here. And we get the tangent matrix as SciPy matrix, sparse matrix. And then we can solve the system, the adjoint system, with our favorite linear solver in Python to obtain the adjoint state. Okay, so these new bindings are really useful. Now I will just show a short example of an application in augmented surgery. So it's the same thing. In augmented surgery, we have, before the operation, we have made a CT scan or magnetic resonance imaging to obtain a mesh of the patient's liver. During the operation, we film with a camera the surface of the liver, and we get a point cloud that represents its visible surface. And the objective is to compute a volume deformation to have some nice images like on the right to show to the surgeon so that he has an idea where the tumor is, where the blood vessels are. In our test case, we will use a mesh and point cloud that are available on the Sparse Data Challenge website. They were made with experimental measurement on a silicon phantom. Here, note that the point cloud is supposed to match the top face of the mesh, while the surface loading is applied only on the bottom face, like below the face we don't see, of the mesh. After an initial rigid registration, we run our adjoint method with a limited memory BFGS, so quasi-Newton method that is available in SciPy. Let's just have a look at the convergence statistics. We see that the objective function is well decreasing along iterations, and the optimality conditions they oscillate much because the objective function is not obviously not convex, but there is still a decreasing movement. So much things should be done to improve this convergence, but it is out of the scope of this presentation. For now, we have a fully functioning adjoint method in Python and so far Python 3. It was the objective of the presentation. So to conclude, I show how to implement an adjoint method without putting the hands in SOFA. We use some Python bindings to assemble and extract the stiffness matrix in Python. And I'm pretty sure it might also work with time-dependent problem, though it might be more tricky. That's all I wanted to say. Thanks for your attention.
Thanks a lot, Guillaume. Right in time for the 10 minutes. To keep the time and to avoid overpassing too much the time and to allow people to go to lunch or to dinner if you are in the, I would say, more eastern part of the globe, I suggest we can split directly into the rooms. I'm gonna I have questions for each one of you. So anyway, I'd like to and that's what happened to the previous session, moving from one breakout room to another. I think everyone did that. So do not hesitate to, so I'm gonna share my own screen now. I will just to show again the room sharing, how it's gonna be done, so that you should be seeing my screen now. So we've got presentation from Philippe, Arnaud, Ziqiu, and Guillaume in the right order. Obviously in the same order, we're gonna have room 1 with Philippe, 2 Arnaud, 3 Ziqiu, and 4 Guillaume. So join them in the breakout rooms. You're going to have time for like 20 minutes to ask them all the questions you will have, and then so that's in the breakout rooms. In the meantime, you can always vote, as we said before, and they're going to be I'm sorry. Then there's going to be a break time for lunch, and we're going to restart around at 1:15 sharp, so that then other presentation can start right on time. Okay,